My name is Donia Chaiehloudj. You don't have to remember my last name. My handle is Donia CLD, and I would be more than happy to connect with you on Twitter, LinkedIn, and other social medias. Today, I will talk about TinyGo and how I used Go to actually monitor my henhouse and using the TinyGo compiler. I will cover what is my ideal henhouse. I will do a brief introduction of TinyGo with a bit of theory, and then I will do a live demo so you have a grasp of what is actually TinyGo and how you can use it. And I will wrap up with the things that I learned along this project and what are my next steps. First, let me introduce you my hens. At the front, we have Bleuette, and at the back, we have Francine. And you can see their hen house. Actually, the hen house is partially automated. We have an open and closing door, but I bought this system. And I wanted to upgrade the hen house by building something by myself, and I'm a Go developer. To do so, the first step was to monitor the temperature and the humidity, because it was a very easy step to begin with, and to visualize these metrics in a pretty and easy way. So looking at graphs was the best way to do it. I'm going to go into TinyGo and what is TinyGo to give some context and setup first. So TinyGo is a compiler for the Go programming language, but for smaller kinds of systems. And now you might wonder, what are small systems? It can be microcontrollers. For the one that don't know what is microcontrollers, it's like small computers, like tiny computers, where you have memory size that is limited and a little CPU on it. And basically, it looks like this. Like, this one is pretty fancy, actually. There is a screen and stuff, but it looks like this. I'm just going to show it on camera so people on the video will see it again. So this is the microcontroller. And currently, TinyGo is supporting 86 boards, different microcontrollers. There are so many on the market currently. But you can use TinyGo with this kind of boards. You can also use it with WebAssembly. But so with WebAssembly, you can build actually Go programs and use after WebAssembly for servers on Edge, for example. And because TinyGo is building very small binaries, you can also use it for command line interface, like a small program that you might need. And in my case, I'm using TinyGo because I'm using some microcontroller and some hardware, and I needed to build very small binaries to run my programs and monitor my henhouse. Before going into detail about the compiler, I wanted to share a bit of history, how an open source project like this can actually appear, like in the open source world. At the beginning, Eik, which is the initiator of TinyGo, explored some existing projects because he wanted to let blinks on a cube. It was like for a fun project. And he tried MicroPython that is working also for microcontrollers, but it was too slow. Like the LEDs were not blinking enough fast and it was not working. So he decided to explore also other projects that were doing some stuff in Go, but it was not satisfying exactly his requirements. So he just decided to write a new compiler for Go. That's why the 1st February of 2019, the first version of TinyGo was released. And 3 days later, Ron Evans, one of the main contributors of TinyGo, presented it at FOSDEM conference. At the end of this year, TinyGo had so many stars, contributors, and commits. It was the beginning of a rising project. And now people are using it for side projects, like my hen house, but also like here for Game Boy Advance game with Gophers by Aurélie Vache. There is a tutorial if you want to check. And it's even used by the industry, but more for WebAssembly. I know that there is one startup that is using it for embedded system for satellites to test them on the ground. So TinyGo is a compiler. And a compiler, you can say it's different layers transforming Go source code into an executable binary. The first box, the red one, is actually the layers of the Go compilers. You might know that Go has its own compilers and its own libraries to actually build its own Go code. And TinyGo added another layer between the Go one and the executable binary. It's called LLVM. And LLVM is a collection of modular and reusable compilers and toolchain libraries that you can use to optimize the code. So they added this layer to optimize between the Go and the executable binary more and more, so that at the end, the binary size is very limited and very small. Let's see that in action. So here is an example of a very basic program, println hello world. And we are building it with Go. And when I build it with Go, the size of the binary is 1.8 megabytes. Nothing abnormal here. And when you build it actually with TinyGo, the size is 29 kilobytes. Can you see here the huge difference that there is? It's very significant for the embedded world, because the memory size, again, is limited on very small chips. We'll see that after in the demo. Because we are Gophers here, I wanted to share the difference between Go and TinyGo and how TinyGo is compatible with the Go ecosystem. Here is a list of some features. So concurrency for the moment is, at the moment, is fully compatible. You can use Go routines, and they are actually transformed in the LLVM layer in coroutines, so you can use Go routine as you want to. Don't forget that it's different than parallelism, because there is only one CPU most of the time on microcontrollers. So you cannot run different threads on different CPUs. The reflection is in progress. There is actually one PR that is open on the project, so it's partially supported. For example, you cannot do JSON serialization, which can be boring when you're using HTTP and you have your stricter with your JSON fields, But it's a work in progress, and you can contribute if you want to. The third feature that I wanted to talk about is the garbage collector, because I think it's pretty important in Go. So it's a very naive implementation. It's a new implementation of the garbage collector. And what it does is it's more allocating memory until the heap is reached, and then it's freeing it. It's very basic. And you have several options to actually customize it. The first option is garbage collector to none. Pretty dangerous, isn't it? So you're going to not allocate any memory. It means that if you're actually allocating memory in your program, it's not going to work. You're going to have an error. So you're wondering why you're using it. Yeah, but if you have a program that is not allocating memory and it's just doing basic thing, you could use it. The second option is leaking. It means that you're going to allocate the memory, but never free it. So, for example, if you have small programs, again, it can work. But if you have larger one, it's probably, again, going to fail somewhere. And the last one is garbage collector to conservative. It's the more standard one. It works on all the code that you want to write and on all the chips. And it's just allocating the memory with a mark and sweep system. And yeah, it's the one that I use by default. And finally, about the standard libraries. So TinyGo has duplicated standard libraries. So you have the TinyGo one and the Go one. The TinyGo one are not fully implemented. That's why there is some difference between Go and TinyGo. And you can see, actually, all the libraries that are supported by TinyGo. So for example, if you have a Go program and you want to build it with TinyGo to be lighter, it will depend on the library that you are importing, and also the indirect ones. So you can check on the documentation of TinyGo. There is the list of all the standard libraries, if they are supported or not, and also if they are passing the unit test, because they can be OK in the imports, but the unit test can fail. So be careful with that. For example, NetHTTP is not supported. So if you have a Go program with NetHTTP, it's probably not going to work because it's embedding other libraries indirectly, like cryptoRSA, and it's not supported. We have seen a lot of theory right now. So let's see a little bit of practice. When you have your microcontroller, you're going to write something on it, a program, so you can actually execute things and process on it. To do so, TinyGo provides the command flash. So I will specify my target, which is the name of my board. For example, I'm using an Arduino Nano 33. This is the name of my board. And the program, or the directory of your program. And TinyGo Flash actually compiles the code on your computer, then it writes it on the chip, and finally it runs it on it. Each time you're going to reset your board, your program is going to start over, and you can actually write only one program on it. And just so you know, this is my Arduino Nano 33 that you can see here. And while I'm flashing it, so I'm writing my program on it, I have the built-in LED, the orange one that is blinking, so I know it's actually writing something on it. So as a developer, you know when you're writing code, most of the time it's not working, isn't it? So you have to debug. And to debug, I'm using println and printf. Do you recall? So what I do when I write a program, and during all this program that I developed for my hen house, I put some logs and printlns in my code, and then I was like, how am I going to read from the standard output from this board? So I checked on the internet, and what I saw was, plug your board on your computer, OK. And then where is the standard output? And I discovered there is a command that is called screen. So I used it, but it was not closing properly the port, the serial port. And what is the serial port? It's the connector by which my device, my board, is sending data to my computer. And I was like, OK, how am I going to read this serial port properly if it's not closed, and I have to reset all the time my board? So I wrote a Go program, because I'm a gopher. And my Go program is running this serial port. So you can find the name of your serial port in /dev/tty if you're on Linux, and in /cu if you're on Mac. And I'm sorry if you're on Windows. So when I found the serial port, I actually connect to it. I'm opening the connection with it. And then I'm just printing the standard output of my board on my standard output on my console. And then when I kill my process, I'm closing properly my port. So I don't have to set up each time, reset my board. Again, let's see in action what it looks like. So here is a very basic program. Greeting you, London, and the GopherCon UK, each second. And when I run it with Go, you can see the logs, like from my console, the two first lines. And the third block is I flashed my board, I wrote this program on it, and then I read from the serial port with my Go program that I wrote. And you can see something here. about the time. So on Go, you can see that the time is the one when I launched like a few days ago. And on TinyGo, it's beginning at 0 Unix time in 1970. It's because there is no synchronization time on boards. So each time, again, you're writing on it, you're beginning at 0. The clock is reset. So be careful with that if you're going to buy a new board. So we use printlns and prints, but we actually have debuggers on our IDE most of the time. How can we do this with actually boards? So TinyGo is providing a debugging tool. I tried it with my Arduino Nano 33, and it was not working. Let me explain. So TinyGo is based on GDB, a GNU debugger. It's also used for C++. It's very basic. I didn't know about it before, don't worry. And you need a debug probe, so actually GDB can read from your board. And most of the boards don't have one. So my Arduino didn't come with, but there are some boards that have. So in my case, I would have to buy another component to do the debug probe, the job of the debug probe. I didn't do it for the moment because I'm fine with my println. And here you have, just one thing that is interesting also is if you're using concurrency, you can actually observe the scheduler and see all the Go routines and the program, how it goes. And below you have an example when you run TinyGo debugger. With the target here is microbit, and it's another board, kind of board, and it has actually a debugger probe on it. And at the beginning, the program is just halted, and as any debugger, you can add breakpoints, you can pause, you can continue. You know all the basics about TinyGo and microcontrollers right now. So let's go back to my project and how I'm using TinyGo. Here is the electrical circuit of the material that I'm using to monitor the henhouse. First, I have the Arduino Nano 33 IoT that I mentioned. And IoT is very important because it means the board has a Wi-Fi antenna on it. And you're going to see after how important it is. Then there is the DHT22. It's a sensor for temperature and humidity. It's a very basic one on the market that you can find. And there are 3 wires. The first one is the data, because the Arduino is going to ask for measures the DHT, and the DHT is going to answer. So we're sending bytes here. The second one is the VCC, which is the power supply for the DHT. And the third one is the ground. And you can see in real what it looks like. It's very, very simple, isn't it? Like 3 wires, 2 components. My Arduino and my DHT are based in my henhouse. So there is a program running on it asking for measures. And in my house, I have my computer. I'm running a Kubernetes cluster where I have a Go web server that is waiting for new measures from the DHT and the Arduino. And I have a monitoring layer, because I told you I wanted nice dashboards. So I'm using Prometheus and Grafana here. First, when I developed at home, my Arduino and my system was working. But then I moved my Arduino actually in the henhouse, and it was not working anymore, because the Arduino was not receiving any Wi-Fi signal in the back of the garden. So I had to add a new router access point. And the router access point below the henhouse and the router at home are communicating through a power line. All along the garden, I have a long cable for the moment. This is my production environment. So you can see on the first picture, below the hen house, I have my router access point that I just mentioned that I had to add, and the power line and the power supply of the Arduino also. The second picture there is Francine, and the Arduino that is protected, and the DHT. I told you that there is a program running on my Arduino, so I'm going to explain what it looks like. First, I'm using some libraries from TinyGo, the TinyGo standard libraries. I told you it's like the same as Go, like FMT and time, you know them, pretty basic. But machine is a TinyGo specific package that lets Go know how to talk to the board. So it's doing this abstraction that you're not setting instruction in bytes, but just saying like, I want to set up a new LED, a new device. And then I'm using the TinyGo drivers library, and it's mapping hardware commands from like interfaces. So for example, the DHT, I'm using dht.measure. I'm not saying 0x01 asking for a data. So I don't have to manipulate bytes, but instead I'm just like using interfaces and Go, which I like. And then I'm using also net to send HTTP requests and Wi-Fi Nina to actually use the Wi-Fi and connect my board to Wi-Fi. So I'm not showing here the full code, but you have my GitHub if you want to check what it looks like. I'm just like putting some pseudocode here. First, in my main, I'm setting up my device. So saying the pins on the microcontrollers that I'm using, my SSID, like for Wi-Fi, you know, all the setup stuff. Then I'm connecting to my access point to the Wi-Fi. And then each 10 seconds, I'm going to ask my DHT, my sensor, for new measures. I'm retrieving the temperature, the humidity, and an error. In case of an error, I'm just printing it and ignoring it. Otherwise, I'm sending these measures through HTTP to my web server on my cluster on my computer. We all probably know in this room how to write a web server. So I will not go into details, but if you are a newbie, please go check my GitHub. The only thing that I wanted to mention that is important for me is the Prometheus data that I'm using. So Prometheus Go client lets you define different type of data and metrics. You can use, for example, histogram. And here I'm using gauge. I'm setting the temperature in Celsius and the humidity in %. I'm registering them. And each time I'm having a new request coming, I'm setting these values so then we can see them on Prometheus and Grafana. This is the full infrastructure here. Again, we have the Arduino sending HTTP request to my cluster. And I needed an Nginx to expose my web server outside of the cluster because they couldn't communicate otherwise. And I'm instrumenting this app, this web server, with a service monitor from Prometheus, so I can actually scrape the app metrics, the sensor values, temperature again, and humidity. Then sending them to Prometheus, and finally to Grafana, so I can have dashboards at the end that I can see. This is demo time. Let's pray together the demo God. So first, what I'm going to do is flash my board. So as I told you, I'm going to write my program that is asking for the measures on my board. So let's do it. And maybe we can see here. the orange LED here that is blinking? Okay. Oh, sorry. And it's successful, yes. So I would like to see you something here. So I have some device information. Here is the type of the chip on my board. And here is the total size of the memory that is available on my microcontroller, 256 kilobytes. If you remember, the Hello World built with Go was 1.8 megabytes. I cannot write a Hello World on my microcontroller if it's built with Go, because it is embedding so many useless libraries that I don't need in this code that is so heavy. So now we have seen this. I want to check my serial port. I'm going to read from it, and I have some logs and printlns that I left for the demo here. And I'm using the program that I wrote here, and I'm specifying my port. It's CU USB 4001. Depending on where you plug it, it changed the name. And here we can see several interesting things. So here's the number of requests that have been sent since my Arduino has been flashed. Then I have the time. Again, it began at 0. So it has been like 1 minute I'm talking about the things about TinyGo Flash. Then we have the temperature and the humidity that have been retrieved from my DHT. And here I'm sending the request to my web server. And my cluster is actually deployed on my computer here. Now I want to see on the other side, on the cluster, what it looks like. So I'm just going to kill this and check the logs from my pod that is containing my web server. So let's see what it looks like here if I'm receiving measures. Yes. So I'm in UTC time, by the way. Is it? Yeah. So we have 1 hour difference. And you can see. Question. So here what you can see is the logs from the web server. We have the new request that came from the Arduino on it. And it's printing the gauge that are set up for Prometheus, the temperature and the humidity values every 10 seconds, almost 10 seconds. So you have seen this. Let's see the last part. This is the graphs. So you can see on the graph the current humidity and temperature. So we have the minimum value, the average one, the maximum one, and the last one in the interval that is set up here. I have the same thing for the temperature, and we have the graphs that are live. And just there are thresholds. So the thresholds are just informative for me to know, for example, if it's too hot, I'm just going to check my hands, if there are enough water. If it's too cold, maybe just to pamper them, you know. And below you have the tables. It's just for debugging. I used it because I found it easier to see all the values and check with the DHT if it was corresponding. Now I'm going to make the temperature and the humidity increase by blowing on the DHT. So here we have, as you saw, the DHT here that is plugged to the Arduino. So let's see what it looks like here. Just, you know, the sampling of Prometheus is 30 seconds, and I'm sending every 10 seconds a new request to the DHT, so I have some values that I'm missing. But let's see. It can take like a few minutes, but that's OK. Let me blow again. And we can see here, nice. So we have 89%, 92, yes. So we can see here the graph. So you can see that it's actually working. I'm not lying. And we have the temperature. And so on this sensor, the temperature is less sensitive than the humidity. So you're going to see like the value increase a lot on the humidity, but on the temperature it's going to be like a few degrees. So just, you know. Okay. I hope you enjoyed the demo. So let's wrap up now. The things that we've learned today. So TinyGo is a Go compiler for small places. Small places can be microcontrollers. It's any place where the memory size is limited and you want to build a binary with a very small size. If you want to use it for microcontroller and have fun with it, you can flash. And using the TinyGo flash command, precising your target, because it's important for the architecture there, with the name of your board and your program, or the directory with all your programs. TinyGo drivers examples are a treasure chest. I use them a lot at the beginning before like moving things around. They can have bugs. But the first time when I used the DHT, I actually fixed it, and it was the first time that I could contribute to TinyGo. And I was very happy like, to be a contributor of TinyGo for the first time, you know. So that's also an interesting way to contribute to projects, open source projects. I do not have any strong hardware recommendations here, because I don't know so much like about all the boards that there are. But I saw on Slack, Daniel Esteban, who is another TinyGo contributor, said that boards with architecture SMD 21 and 51 are very well supported by LLVM and TinyGo. Not, for example, the Arduino Uno. There are many problems with LLVM, so you know. And Arduino actually had a new board, just launched a new board, the RP 2040, the Raspberry Pi 2040. And it's working also very well. You can do new features with the last version of TinyGo. It's very funny. And if you don't want to invest, that's OK. There is a TinyGo playground. And like Go, you can play with code, and you have the boards live, and you can play with LED, add cables, and stuff. So you can just have a look at what it looks like. As Gopher, you have all the skills now to enter the IoT world. You are a Gopher, you know Go, you now have basics about TinyGo, and even with your IDE, if you have VS Code, there is a plugin. If you have a Golang also, and sorry for Emacs and Vim people. As you have seen along this project, it's pretty experimental, and I would like to improve it. So here are some steps that I could use. The first one is I don't really need HTTP, so I could use asynchronous protocol like MQTT, and there is a driver in TinyGo. And I'd like to get rid of the long cable in the garden, so I want to invest in a long-range Wi-Fi board. And probably power supply my Arduino with a solar panel, maybe. I brought all my stuff here. I have my router access point that is just here below me. And I have my Arduino and my DHT. So I would like to deploy my app in the cloud so I can show actually what's going on my hen house live. And even when I'm leaving house, I can check. A long story, but short story. When I began this project, we had 3 hens. And you know the end. The fox came, and I'd like to add a fox detection system so I can avoid, again, these kind of situations. Thank you to the TinyGo community that helped me a lot, my friends and partner. It's not a lonely project that we are talking about here. And I would love to connect with you on social media again and talk about TinyGo and Go. You can check my GitHub if you're curious about how to deploy and how to use TinyGo. Thank you a lot.